Good morning, everyone. So far, the conference has been pretty intense. So this morning, I will do a very relaxing talk with some experimental findings about a particle cover interface. So this work has been done with my two PhD students, Ilyes B. and Emric Roux, and with my collaborator, Alexis Duchesne and Farzam Zoeschag. So when you add some particles to liquid-air interface, you can get some very, very interesting and original property, let's say. So some examples are here. You take some droplets, and you will take some partially wettable particles. So some particles that like to be at the interface between liquid and air. And if you cover your drop with these particles, as was shown by Oscillus and Curie, these droplets won't stick to the surface anymore because the liquid is no more in contact with the surface. So they can roll and bounce over the surface. Then, if you take here, what you see is in fact an air bubble inside a liquid. And you can see that this air bubble here remains non-spherical. And this is really stable and very stable over time. So you see, if you cover this bubble with this particle, you can sustain non-spherical shape. One last thing is this bubble. You can, in fact, we have some bubbles that we created like a few years ago, and they are still alive. So when you put these particles on the surface, you can arrest dissolution. So the dissolution will be stopped, and I will explain later on. We come back to that. Yes. I have one bubble, one of these cylindrical bubble. I kept it for 1 year and a half. Yeah. And I will be talking about a long-lasting bubble just after. So I have 3 sections, and the second section is about other long-lasting bubble. So now I will start with reverse Safman-Stellar experiments. So you all know, I think I don't need to talk a lot about this, that if you pour a less viscous liquid into a more viscous liquid, so here it's water that is poured into glycerol, then you have this Safman-Stellar instability occurring. And I think I don't need to spend a lot of time to explain to this community because you are all familiar with the Safman-Stellar instability. But basically, when you have less viscous liquid that is poured into a more viscous liquid, then if you create a small perturbation, the resistance to the flow in this direction will be smaller than the other direction, and you will have the instability developing. But if you do the reverse experiment, where you pour a more viscous liquid into a less viscous liquid, then normally it should be stable. So if I take water and I pour it in air, there shouldn't be any instability. But the question we were interested in is what happens if we add some partially weighting particles on the surface of the cylinder. So basically the experiment is very simple. We just have LHO cells. We introduce some liquid at the middle of this cylindrical container, and we push it at a certain flow rate. So the flow rate here is very slow. It's 2 milliliter per hour up to 2000 milliliter per hour, so very slow. The distance between our walls is typically 100 micron to 1000 micron. And the capillary numbers that compares viscous diffusion to capillary forces is very small also, which means that capillary forces are dominant in our problem. Of course, the Reynolds number at this flow rate is very small also. So capillary forces are strongly dominant in our problem. The particles that we have are around 15 microns, so there is no Brownian motion. And this is some partially wettable particles with typically a contact angle of 70 degrees. So let's see what happens. So we have this experiment where we have some particles dispersed on the two surfaces of the cylinder, and we pour some liquid. Well, if you do that at low concentration, and at least at the beginning, it's stable as you might expect. But if you increase the concentration to higher concentration, then you have some fingers that are appearing like this and that are developing in your system. So if you do it at very low flow rates, here is 20 milliliter per hour. This is some random, it's going relatively random. If you increase a bit the flow rate, then you will have some fingering that will be with a more radial shape. So we did, in fact, of course, many experiments, and we changed the concentration of the particle, we changed the flow rate, and we changed the distance between the walls. So this is a nice diagram from my student. I don't know how he was able to do that, but basically, if you take, for example, this experiment here, so this is an experiment that is done with a pretty strong concentration and small flow rate. Then, if you increase, for example, the distance, you see that the fingers are becoming larger. Then, if you go in this direction, if you increase the flow rate, as we have already seen, you go from some fingers that are pretty random to something that is more radial. And finally, we discussed that, and if you change the concentration, you see that the size of your finger is also changing. So we wanted to understand that, and to understand that, what we did, our guess was that the instability comes from the fact that the particles desperately want to be at the interface of our meniscus. So the idea was, at the beginning, when you pour your liquid into these particle-covered surfaces, you have some space to integrate the particle over your meniscus. But at some point, then you won't have any space to incorporate these particles. And if you have no space, one easy way to create some spacing for this particle is, instead of having this regular circular shape, to create some fingers, because you will have, of course, more surface compared to with the same volume. To test this hypothesis, we simply computed the space that we have when you have this meniscus. So you take a constant mean curvature surface, you compute the surface here, we made some approximation to get some analytical formula, and then you compute when you will, depending on the concentration of particles on the surface, when your meniscus will be completely covered. And you get a critical radius when all your meniscus will be completely covered with this particle. And this is what we did, and we did it for a lot of different concentration and on heights and so on. And what you see, the points are some experiments done with different parameters, so concentration and height. And what you see, the lines are the model. So we have two lines for the model, because something that we do not control very well is the wetting properties of the wall, because of course when you pour some particles in it, you can modify a bit the surface cannot be so clean, so you can have some variation in it. So we did it for different wetting angles, but basically you see that we are able to reproduce the time when the instability occurs pretty well. So this means that our explanation that the instability occurs when you have no more space to integrate the particles seems to be correct. So then, what fixes the finger width? So if you're in radial configuration, it's a bit complicated configuration. So we went back to a much simpler configuration that is a rectangular channel. So here you have again some liquid, you have some particles that are dispersed. This time this is in a rectangular channel, and we just push our liquid font inside this rectangular channel. So it's slow experiments, even if it's speeded up a little bit here. So the meniscus is here. So at the beginning again, we will collect the particles that are on the surface, and you see that once the meniscus is completely covered, again, you have a fingering instability occurring. And if you do the experiment in a long channel, in fact, you get a finger width that is pretty stable. So again, the idea is this finger width, in fact, correspond to the exact surface that the exact width that you need to be able to incorporate all the particles that you will be able to encounter. And if you compare this time the width of our finger as a function of concentration, and you again take just the formula that the finger width is fixed by the criterion that you want to be able to incorporate all the particles into your meniscus, you are able again to recover the finger width. So the conclusion of this first part is that you see that just by incorporating particles in your program, then a stable situation can be turned into an unstable situation by the simple presence of microparticles on the walls. So just something that I didn't discuss here is that all this criterion works very well when you are at low flow rate. So the red point on the red curve correspond to low flow rate. But of course, as soon as the flow rate increases, then you have also a role of the flow. This is why it's becoming radial. At the beginning, it's not radial because there is no preferential direction. But if you have a flow that becomes more significant, then you will have to take into account the flow. And this is something that we did not look at the moment, at least from a... Okay, so the point is, the particles that we have are partially wettable particles. Okay, so if you look at their minimum energy is not when they are in air or when they are in liquid, they are when they are in the interface. When you are pouring your liquid at the beginning, you have in fact a meniscus that will have, at least from the top, a circular shape like that. Okay, so you have a certain amount of surface compared to the volume that you have. Okay, at the beginning, so you pour your liquid, you will collect the particle on the meniscus here. Okay, but at some point, if your interface does not grow sufficiently rapidly compared to the number of particles that you encountered, then you have no more space to incorporate the particle. So the idea is that to create more space for your particle, you will create this complex shape that will increase for the same volume the surface that you have to incorporate particles. So really the instability just comes from a fact that the particles want to be collected at the interface. They don't want to go in the liquid or in the air. They want to be collected at the interface. So if you have no space to incorporate them, then they will make you create some space. Then you have no instability. Yeah. Exactly. This is the case that you have here. Here, in the first case that I showed, you have particles, but you create more surface than needed for the particles, so it remains completely stable. Okay, so now let's move to, you were saying that we were keeping bubbles for a long time, and in fact we kept some bubbles for a very, very long time. So the bubbles I will be talking about, I think the longest that we have are now 2 years. So, okay, this is a completely different problem. This time the question is about soap bubble bursting. So I guess that you have already all seen this kind of videos where you have a soap bubble, and after some time, if you leave your soap bubble, then it will burst. Why is it bursting? Well, there are in fact 3 reasons why the soap bubble can burst. The first reason is if you look here on this image, so you had a bubble that we created, and you wait for some time, so you can look with a colored camera at the interference fringe, and from the interference fringe you can measure in fact the thickness of your film here. And if you look at the thickness of the film, you see that the thickness of the film is going to a very small value here, up to here 2 microns at the bottom. And why is it? Just because, of course, you have drainage. Because of gravity, the liquid is going from the top to the bottom, and so the top of the soap film becomes very, very thin. If you want to make a sandcastle, you will mix the liquid with particles, because you will create some surface tension bonds, and these capillary bonds will maintain the integrity of your castle. So the idea was to do the same, but the opposite. We have our bubble, and we will add some particles to our liquid to prevent drainage. How were we able to do that? Well, we simply did this kind of experiment. So you can all do that in your kitchen. You can do it with cinnamon if you want to eat them after. And we were even contacted with some people doing some cuisine, asking, can we do some bubbles that we can eat? But you can do indeed. So you just disperse some microparticle on the top of the liquid, so it will create a raft. Then what you will do is just inject some gas below your particle raft. So you obtain here your bubble. And then you just have to push the bubble a little bit so that it's completely covered. So it cannot be simpler. If you want to do it at home, it's very easy. You just need some cinnamon and you will be able to do that. So then you just have to take it. Yeah, these bubbles are as, this is very funny story. We wanted to make some flying everlasting bubble, but we were never able to do that. The problem is here the particles are quite heavy and so it will go down. So we bought some helium to try to do it, but even we didn't find, light enough particles to make them fly. I think this is possible. You just need to find we bought in fact some, what we bought is, you know, there are some microparticles that are just glass shells. And they are very, very light, in fact, because the glass shell is very, very thin. And so we wanted to use this kind of glass shell, but for that, they need to be partially wettable. So we need to functionalize their surface so that you decrease the wettability. And in fact, the problem that they are so light that when we tried to do some chemical operation with that, we were not able to do it. So at the end, we were not able to do flying bubble, but I think definitely this is something that you can achieve. Yeah, that will be nice. The only thing is that unfortunately, I have Farzam in my lab, and Farzam did a lot of microgravity experiments. And the thing that I learned about microgravity experiments is that you spend 3 years to do an experiment. Then you have 4 points on your graph, and then I'm not sure the investment is the time over. Yeah, exactly. So if you want, what I have learned is that if you want to do a nice flight for once in your life, then you have to ask for that. But otherwise, it's not very efficient in the number of data that you get. Yeah. Yes, you can do a bubble bigger, but you are still limited by something. Here, when you create the bubble here, when you do that at this moment, then the liquid, at this point still there is a small drainage when you create it, and if you do that with too large bubbles, then you have troubles to create it. So the problem is really the creation more than the stability. I think you could be able, but with this technique, it's complicated. In fact, I got this idea to create this, because in fact, if you go back to my first slide, I got this idea to create this kind of bubble a long time ago because I saw this graph, I made this graph. You had droplet, you have bubble in air, so what was missing was the soap bubble. So I got this idea in 2010, but my student wasn't able at that time. I got a master student on that, and we were not able at that time to create this armored bubble. And unfortunately, when I was able to do that, we were very happy, but we went back to the literature, and there were another group that succeeded with a completely different technique to do some armored bubble like that. There is some difference in the fabrication, and one big difference is that in their case, they need some surfactants. So here they have some surfactants, while we don't have any surfactants. So this makes a difference because in their case, if you inject some air inside your bubble, because of the surfactant, even if the particles distance increases and you have some film in between, it will remain stable. So you can increase the pressure inside, and at some point it will increase the distance between the grain, and it will still remain stable before bursting. In our case, you don't have any soap or any surfactant, so as long as you would try to increase and create a liquid film in between, then you will keep. Yes, it looks like Pickering emulsion is indeed exactly that. You have some particles covered. Here it's just that it's air in both sides, while in Pickering emulsion you have some droplets surrounding by liquid and particles at the surface. Yeah, it's different from first effect. So, but something that was that nobody looked at is what is the lifetime of this bubble. So here you have this same particle covered surface bubble. And we just added some ink to visualize where it is. Of course, if you had no particles on the surface, you could look at the drainage time as was derived by Pierre-Gilles de Gennes. And the lifetime this will be around 20 microseconds for such a big size bubble. Yes, this is why you will never observe bubbles if there is no like dirt or surfactant or anything. You will never observe pure water bubble. You can observe bubbles with surfactant or with dirt or something, but not pure water bubble because the living time will be very but here with our bubble, so this is a bubble, and we look at the evolution as a function of time. And this, you see that the bubble lived for quite a long time, 64 minutes, before you see that it's going down, meaning that the bubble has opened. And you see also that there is something going on because the color of your bubble has changed. So what we did was measuring the mass of your bubble as a function of time. And you obtain these very nice curves. So sometimes people are saying, no, this is not true data, but this is true data. These points are experimental data. So you have the evolution of the mass of your bubble as a function of time. And what you see is, of course, that you have something going on here. You have a decrease of mass, and at a certain point, you reach a plateau. So as I said, this bubble, we were able to suppress drainage, but there is yes, something that I didn't tell. So here, the bubble lifetime is increased. And why is it increased? Because you create some capillary bond between your particles and your liquid, and the capillary bonds turn what would be a high bond number surface, if you compute it over the big surface, to a small bond number of these capillary bonds. So at the end, you are no more sensitive on your drainage, and you succeed to suppress drainage. But you still have to cope. I said, one first thing to kill the bubble is drainage, the second is evaporation. And this is what we see here. So the bubble mass is decreasing because of evaporation. And so at some point it reaches a plateau, which means that there is no evaporation going on anymore. And you see that if you look at the point where the bubble opens, that is here, so this red point, is this purple, no, let's say purple, yeah, purple point, you see that the opening of your bubble occurs slightly before you have evaporated all your liquids, okay? Of course, we did a lot of experiments, and we did experiments with many different ambient humidity. And in all these cases, you see that the mass is decreasing. Of course, it depends on the humidity, also depends on the initial content of liquid in your bubble. But eventually, in all cases, your bubble will die. A proof that it's dry also is that if you wait for some time, you will see that the bubble will collapse like a sand pile. So it means that there is no more some liquid bridge between your particles. So as I said, we were able with this water droplet to suppress the effect of gravity by creating some capillary bridges, but we were not able yet to suppress evaporation. And this is why I asked my question to you, Jean-Pierre, last time. Is because, in fact, when you manipulate glycerol, when you do experiment with glycerol, you better be careful. Because you think you have glycerol, but if you are not careful, you have no glycerol anymore. Because the glycerol is a hygroscopic liquid, so it has some hydroxy group, a lot of hydroxy group in this molecule, and it tends to create bonds with water that is contained in the air. So if you take glycerol and you wait for a long time, you have no more glycerol, but you have glycerol plus water, okay? So glycerol is a very efficient liquid to attract the vapor that is contained in the air. And so we redid our experiments, the same with the microparticle, but this time we have no more just some water, but we have some water-glycerol mixture. And look at what happens. So if you have a small amount of water-glycerol mixture, you see that your bubble, as previously, the mass is decreasing, and at some point you will break your bubble. If you then increase your water-glycerol above a certain threshold, you see that at the beginning, the mass of your bubble is decreasing, but then you are reaching a plateau, and then your water mass does not evolve so much as a function of time, so you reach a plateau of your mass. And if you start with a very strong amount of glycerol at the beginning, you see that here is 19% of glycerol in your bubble. You see that on the opposite, instead of decreasing, the mass is increasing. Why? Because you are absorbing the water that is contained in the air. So with this kind of bubble, with this kind of mixture, we were able to keep our bubble for 65 days. And in fact, the funny thing is that we submitted the paper, it was accepted. No, it was in a double review, but with small revisions. And just in the revision process, the bubble died. So we had to report that it was not everlasting bubble, but it was still bubbles that could die. But the reason that they died has nothing to do with physics. Our bubble starting to be green because glycerol is something that, bacteria and so on I like, and there were some life developing in our bubbles, so we had some biological bubbles. Sorry? It was murdered. Yeah, it was murdered by bacteria. So the proof that it's still regularly, we made many of these bubbles, and the proof that there is still some liquid is that sometimes we puncture them, and you see that they have very, very different behaviors and then they are dry, because you have these liquid bridges between your particles. And this is something that would be interesting to look at, is the dynamics of this kind of interfaces. Okay, so the point is, can you predict the bubble evolution? Well, we made a very simple, toy model. So basically, we just say that the evolution of mass of our bubble is the absorption of the liquid minus, due to the glycerol, minus the evaporation. And basically, your absorption will be proportional to the humidity, so the quantity of water that you have in air, and will of course also be proportional to the content, the glycerol concentration. While the evaporation on the opposite will decrease as you increase the humidity up to 1, where you will have no evaporation anymore. And it will be proportional to the water content, and the water content is 1 minus the glycerol content. So this is a very simple toy model. But you have of course, two constants to determine here. But the good point is that you can determine them from experiments, so you don't need to introduce any constant that will not be determined. How you do that? Well, if you take the pure water experiments, then you have the evolution of mass. Of course, this time you have only water, so you have no glycerol anymore. So if you have no glycerol, you have no absorption, you have just evaporation anymore, just evaporation. So you end up with just the evolution of mass is Ke 1 minus IH. And we had all these experiments with water, so you can determine your constant for the evaporation. What about the other constant? Because you have two constants in the problem. Well, to determine the other constants, or in fact to determine the ratio between the two constants, you come back to your model and you look at the equilibrium situation. At the equilibrium situation, here you have no more evolution of mass, and you end up with this equation at equilibrium. And you have the glycerol content that you can relate to the relative humidity. And the point is that is very well known, so that you can find anywhere. You have some nice points here that tell you, as a function of the relativity humidity, how much glycerol you will have, glycerol and water you will have in your solution. And this is with our simple toy model. This is the data that you get in the literature, and this is the curve that we get with this very simple model. So it fits very well. And by doing that, you can find the second constant that was missing in your model. And the good point is that, so you have no adjustable parameter in your problem, but you, the curves that you see in black are what we obtained with this very simple model. And I think that for a toy model, it's quite good agreement with the experiments. So now you are able to predict the evolution of the mass of your bubble as a function of time. But since you know how the mass evolves, if you say that the bubble will die when the mass of liquid will be under a threshold, you can predict if your bubble will survive or not. So depending on the initial glycerol mass ratio and depending on the relative humidity. So we made many experiments with different relative humidity and different initial glycerol mass ratio. And in some cases, you have systematic rupture. In some cases, you have everlasting bubble. And in some cases, you have bubbles that die and some bubbles that don't die. When I say that, it's because we are, of course, not doing experiments on one single bubble. We are doing them on, I think it's 12 bubbles each time for each glycerol mass ratio and relative humidity. So you have this zone. And you see that our model predicts transition between these two zones with the purple line here. So you see that we are able to reproduce the phase diagrams that we obtain experimentally. So the last point is that you can, yes?
So does the life depend on the size of the bubble? I would expect the smaller ones to survive much longer compared to the larger ones.
This is something that we didn't look at, I would say not, because the gravity is no more involved. This is really the evaporation. So either you modified the evaporation process, which might be possible because you change the geometry, but other than that, it's really how fast it evaporates. So if you have the same, liquid bridge volume in between your particles, whatever the size of your bubble, then it shouldn't matter so much.
These are millimeter size bubbles, right?
Yes, yes.
Maybe centimeter, I don't know how big these are centimeters or maybe few millimeters to a centimeter, is that the size?
The size of the bubble here that I showed, so it's, I think you see here, so it's already centimetric, almost centimetric. The diameter is 7 millimeters. So yeah,
I would expect that the weight of the particles to play a role in this.
Yes, you're right that you will deform the particle, but the thing that kills your bubble is not the gravity, it's not the drainage, it's the evaporation. So the question, in fact, that you are asking is the size of your bubble affecting the evaporation process and so on. So on that, I don't. Yes. So not only we were able to do bubbles, but in fact you can do a lot of objects. So we did also experiments on just a flat soap film, and this is we observe the same tendency. If you check just your soap film, then it will die as it usually does. If you add some particles, then you will be able to suppress drainage, but you still have evaporation, so your thin sheet will break after some time. And if you add glycerol, you can keep up your thin film alive for a long time before your PhD advisor, which is me, arrives and pushes the experiment and breaks the film, and the PhD students was Okay, but okay, this one survived before I write in the lab. And you can do also some more complex shape like that. So this is some pyramidal, we just take some frame and created that. And in fact, this one is the one that is one of the bubbles that are still alive. And I think it's 2 years and a half, yes. Okay, so to summarize, so we were able to publish that in Physical Review fluids after being rejected from all natures and so on, because we thought it was a funny story to tell. Hopefully, we had Howard Stone as an editor who found it interesting, put it as the editor suggestion, and then featured in physics, and then it came back to Nature. We made a highlight in the journal. So hopefully, the conclusion is we have to publish in good journals to get a good remark. And the funny thing is, after it was published in Nature, so you have, we had a lot of publicity in all journals and so on, and you can see how the science information is propagating, and it's quite frightening. Because at the beginning, okay, it was like Le Monde, some French journal who were contacting you, and the information was very accurate. It took some time to discuss with us. Then we got to less accurate journal, Huffington Post, but it was still good. It took a few let's say, 1 hour to discuss with us, but progressively it went to Yahoo, blah, 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 and then they asked to some people to comment on that, to scientists, and then it went in all directions, and we were very afraid because some people were starting that you can cure the eye by using this bubble, and I don't understand what they were saying. So we were, at some point, we were afraid because we thought maybe they will say that we can do nuclear reaction inside our bubble. But hopefully, at some point, it's very rapid. The propagation of information, it stops rapidly, but at the end, it stopped sufficiently, so we were safe. And I would like to recognize some nice comments on Twitter. I really like this one. I don't know if you see it. Yeah. So, some scientists didn't like the poesy of our experiments and think it was not very useful, which it might not be, but at least I mean we enjoyed it. I don't know how much time is remaining. I'm done new time. Okay. So I wanted I will just tell that. So I wanted to tell you a story about cylindrical bubbles. So I will just show you the experiments. I don't have so much time to tell you. So what we did is just you push a liquid finger inside air. So this is also a classical experiment. And if you do that, you see that you are collecting the particle here at the surface at the beginning. And again, the same problem. At some point, you don't have any space to incorporate the particle. And so it will create some new space. And how does it? It does it by creating a thin film here at the top of your meniscus. And you see that progressively you are growing a liquid film ahead of your meniscus. And so if you wait for sufficiently long time, in fact, you have liquid, here it's air, so you are creating a bubble because this is liquid surrounding by a film of particle-covered surface. So if you wait for a sufficiently long time, then your bubble is growing, growing, growing. And at some point you see that you have some friction appearing with the walls. And so the bubble will stop. It will become resistant to its displacement. And at some point the pinch-off will occur, and so you will close your bubble. And then you just have to push it out of the tube, and then you get your nice cylindrical bubble. You see here how the film is growing. This is a zoom. If I come back here, so what I will show you is a zoom on this region here where the film is growing, and you see how the film is growing here. You see that each time you encounter a particle, you have a liquid film that is growing on top. So we were able to do some nice cylindrical bubble with that. Of course, all that story depends on the weighting properties of your walls on the particles. So we do many experiments. And we like to vibrate things, so we started to vibrate bubble. So this is a bubble, and we make it vibrate. So you have your cylindrical bubble, you make it vibrate, you see that it's evolving toward a spherical shape. And in fact, the point is that this non-spherical bubble, there are some metastable states. In fact, if you compute the energy, the surface energy, when you have a cylindrical bubble, it's not a minimal superface energy. So if you just vibrate to free a bit the particle, the particle will get out and you will come back to a spherical bubble. And then finally, if you excite it very, very strongly, then you can get rid of your particle from the surface.
Long live India and France friendship.